Section 9.2 Properties of Power Series. This section we will cover geometric series as power series, convergence of power series, combining power series, differentiating and integrating power series. For the geometric series as power series, we call the geometric series in the previous chapter for the fixed number r as of the form the summation of r to the power k from 0 to infinity, or in the expanded form of 1 plus r to the power second plus and so forth. For the absolute value of the r less than 1, we have the sum of the series as 1 over 1 minus r, or from the formula a divided by 1 minus r, a as the first term and r as the constant, the ratio. As a power series, if replace r with the x, we have the summation x to the power k from 0 to infinity, or 1 plus x squared and so forth. And the sum will be 1 over 1 minus x, provided absolute value of the x is less than 1. And this power series converges for the absolute value of x less than 1. So then the interval of convergence is the absolute value of the x less than 1, or x is between negative 1 and positive 1. Convergence of power series. For the power series, as a sigma notation of the ck multiplied by x minus a to the power k, where a and ck are real numbers, x is the variable, ck are the coefficient of the power series, a is the center of the power series. Note the interval of convergence is the set of the x for which the series converges. The radius of convergence of the power series, use the notation r, is the distance from the center A of the series to the boundary of the interval of convergence. To determine the interval of convergence, by the ratio test for the infinite series, as r equals the limit as k approaches infinity of the absolute value of the ak plus 1 term divided by ak term and is less than 1, for the series converges. By the root test, use the notation rho equals the limit as k approaches infinity of the k root of ak less than 1, so the series converges. Convergence of power series. A power series of summation of the ck x minus a to the power k from 0 to infinity, center at x equals a converges in one of these three ways. The first one, the radius of convergence r equals infinity. The interval of convergence will be the set of all real numbers, and the series will converge absolutely for all x. Case 2, for r, which is a positive real number, the interval of convergence will be x between a minus r and a plus r, where a is the center of convergence. And this series converges absolutely for the absolute value of the x minus a less than the radius of convergence r. Case 3, where the radius of convergence equals 0. In this case, there is no interval of convergence, and the series converges only at the center x equals a. Examples: determine the radius of convergence, which is the r, of the following power series, then test the endpoints to determine the interval of convergence. For part A, we have the summation of negative 1 to the power k multiplied by x plus 2 to the power k divided by k plus 1 factorial for k equals 1 to infinity. So the ak is the term negative 1 to the k times x plus 2 to the power k divided by k plus 1 factorial. The series will converge if it passes the ratio test or the root test with the condition. In this problem, we have the terms involving factorial, so it's more convenient to use the ratio test. By the ratio test, the series converges if the value r, which is the limit as k approaches infinity of the absolute value of the ak plus 1 divided by ak less than 1. Since the ak is negative 1 to the power k, times x plus 2 to the power k divided by k plus 1 factorial. We obtain the ak plus 1 as negative 1 to the power k plus 1 multiplied by x plus 2 to the power k plus 1 divided by the quantity k plus 2 factorial, and then divided by ak means multiplied by the reciprocal of the ak, or multiplied by k plus 1 factorial divided by negative 1 to the k times x plus 2 to the power k, and this limit must be less than 1. Next, we are going to simplify this expression by reducing the common factor. For the x plus 2 to the power k plus 1, this is the same as x plus 2 to the power k multiplied by x plus 2 to the first power, where the k plus 2 factorial is the same as k plus 2 multiplied by k plus 1 factorial. We can reduce x plus 2 to the power k and the k plus 1 factorial and k plus 1 factorial. And then the expression behind the limit simplified to be absolute value of x plus 2 divided by k plus 2 less than 1. The negative 1 to the power k plus 1 and negative 1 to the power k reduced to be negative 1. With the absolute value, the negative sign can be omitted. So now, if this limit statement is true, therefore we can rewrite this as the absolute value of x plus 2 must be less than the limit as k approaches infinity of the quantity k plus 2 by multiplying both sides by k plus 2 and take the limit both sides. The limit k plus 2 as k approaches infinity is infinity. So the right hand side term or the limit value will be the radius of convergence. That means the absolute of x plus 2 will be less than infinity, or we can say x plus 2 is greater than negative infinity less than infinity, which is the same as x greater than negative infinity less than infinity. In this case, we can say the series converges everywhere. Or the interval of convergence is negative infinity less than x less than positive infinity. And the radius of convergence is r equals infinity.